Here's a question every programmer eventually asks. If your input doubles, how much slower does your code get? The answer comes down to one idea, big O notation. Say you're searching for a name in an unsorted list of 1,000 items. Worst case, you check all of them, 1,000 comparisons, double the list, and that doubles too. That's linear growth. Cost scales directly with n, the size of your input. We call it ON. Here's the formal rule. We ignore constants and we only care about the dominant term as n grows large. 3n plus 5 operations, we just call that ON, the 5, and even the 3 don't matter at scale. And usually big O describes the worst case, the most operations your algorithm could ever need. But not every algorithm grows the same way. Let's plot cost against input size. A constant time step like reading an array's length barely rises at all, O1. Binary search halves the space every step. Its cost creeps up so slowly it's logarithmic, O log n. Our linear search climbs steadily at the same rate as its input, ON. Efficient sorting sits just above that, ON log n. A nested loop comparing every pair curves upward fast, O1 squared. And brute force algorithms can explode entirely, O2 to the n, exponential. Here's why the shape matters more than the formula. At 1,000,000 items, logarithmic takes about 20 steps, linear takes 1,000,000. Quadratic takes 1,000,000,000, exponential, more steps than atoms in the universe. In your code, one loop is usually ON. A loop inside a loop is usually ON squared. That's why a single extra nested loop can turn a fast function into one that never finishes. And a halving loop like binary search gives you O log n. Big O doesn't measure seconds, it measures how cost grows as input grows. Learn to see the shape of your code and you'll know what survives at scale.